Unique PTR and shared PTR. A tour of C++, Concurrency and Utilities. The examples so far take care of objects defined in a scope, releasing the resources they acquire at the exit from the scope. But what about objects allocated on the free store? In memory, the standard library provides two smart pointers to help manage objects on the free store. 1. Unique PTR to represent unique ownership. 2. Shared PTR to represent shared ownership. The most basic use of these smart pointers is to prevent memory leaks caused by careless programming. For example, void f, int I, int j, pointer to x versus unique PTR x. Pointer to x, p equals new x, allocate a new x. Unique PTR x sp, new x, allocate a new x and give its pointer to unique PTR. If I less than 99, throw z, may throw an exception. If j less than 77, return, may return early. Key arrow operator / access members of a structure through a pointer, do something, may throw an exception. SP arrow operator do something, may throw an exception. Delete p, destroy pointer to p. Here, we forgot to delete p if I less than 99 or if j less than 77. On the other hand, unique PTR ensures that its object is properly destroyed whichever way we exit f, by throwing an exception, by executing return, or by falling off the end. Ironically, we could have solved the problem simply by not using a pointer and not using new. Void f, int I, int j, use a local variable. XX. Unfortunately, overuse of new and of pointers and references seems to be an increasing problem. However, when you really need the semantics of pointers, unique PTR is a very lightweight mechanism with no space or time overhead compared to correct use of a built-in pointer. Its further uses include passing freestore allocated objects in and out of functions. Unique PTR x make x, int I. Make an x and immediately give it to a unique PTR. Check I, etc. Return unique PTR x, new x, I. A unique PTR is a handle to an individual object, or an array, in much the same way that a vector is a handle to a sequence of objects. Both control the lifetime of other objects, using RAII, and both rely on move semantics to make returns simple and efficient. The shared PTR is similar to unique PTR except that shared PTRs are copied rather than moved. The shared PTRs for an object share ownership of an object and that object is destroyed when the last of its shared PTRs is destroyed. For example, void f, shared PTR fstream. Void g, shared PTR fstream. Void user, const string address of name, iOS base, open mode. Shared PTR fstream fp, new fstream, name mode. If not, pointer to fp, throw no file, make sure the file was properly opened. fp. fp. Now, the file opened by fp's constructor will be closed by the last function to, explicitly or implicitly, destroy a copy of fp. Note that f, or g, may spawn a task holding a copy of fp or in some other way store a copy that outlives user. Thus, shared PTR provides a form of garbage collection that respects the destructor-based resource management of the memory-managed objects. This is neither cost-free nor exorbitantly expensive, but does make the lifetime of the shared object hard to predict. Use shared PTR only if you actually need shared ownership. Given unique PTR and shared PTR, we can implement a complete no-naked new policy for many programs. However, These smart pointers are still conceptually pointers and therefore only my second choice for resource management after containers and other types that manage their resources at a higher conceptual level. In particular, shared PTRs do not in themselves provide any rules for which of their owners can read and/or write the shared object. Data races and other forms of confusion are not addressed simply by eliminating the resource management issues. Where do we use smart pointers, such as unique PTR, rather than resource handles with operations designed specifically for the resource, such as vector or thread? Unsurprisingly, the answer is when we need pointer semantics. When we share an object, we need pointers, or references, to refer to the shared object, so a shared PTR becomes the obvious choice, unless there is an obvious single owner. When we refer to a polymorphic object, we need a pointer, or a reference, because we don't know the exact type of the object referred to or even its size. So a unique PTR becomes the obvious choice. A shared polymorphic object typically requires shared PTRs. We do not need to use a pointer to return a collection of objects from a function. A container that is a resource handle will do that simply and efficiently. Thank you for watching.